In this lecture, we're going to be covering 2.6, and we're going to be learning about the names of compounds. This is very important. This is something that we continue to work with throughout the rest of our chemistry careers. So this is something we can't forget. Mastery of chemical names is going to go a long ways in our future. So again, I just can't stress enough that the mastery of naming compounds, what we're learning here tonight, is going to be very important. Okay, so we're going to learn about the names of compounds, starting with ionic compounds. We'll be spending most of our time working with ionic compounds. There's a lot more to naming them. Then we're going to learn about molecular compounds, specifically binary molecular compounds. And then we'll finish off by learning about naming acids. Okay, let's get warmed up with a little bit of review. We're asked to convert 0.0072 kilograms to milligrams. Okay, we have a metric conversion before us. We have one of two possible tools, equations or units, and we're using our units. So that begins with step one. We're after milligrams. That tells us everything we need to know about step two. If we're looking for our answer has a single unit, then we're going to start with a number with a single unit. So of course that's the 0.0072 kilograms. Then on to the beginning of step three, which starts by getting out of that initial unit, so out of kilograms. Getting this far should always be nice and easy. Now comes the big question, can we go straight from kilograms to milligrams? No, we have to go through the base unit. So first in the grams, and then from grams we can go to milligrams. And in our normal fashion, we just took small baby steps to get to our answers units, and that made sure that no step was ever too hard. Now for the numbers. The base 10 number always goes where? With the base units. So in this case it's the grams. The millis, the kilos, the gigas, the nanas, whatever those prefixes are, they get a 1. And now 1 kilogram, like 1 kilo anything, is 10 to the positive third. Whereas 1 milligram, like 1 milli anything, is 10 to the negative third. My original number has two significant figures, and so I'm going to have two significant figures in my final answer. My original number is 7.2 times 10 to the negative 3. I'm going to take that negative 3 and add the positive 3, and then subtract that negative 3 at the bottom. And negative 3 plus positive 3 is 0. 0 minus negative 3 gives us positive 3 for 7.2 times 10 to the positive third milligrams. Next, what is the symbol for silver? Silver, argentium. Remember, Argentina is named after silver, and that's Ag. Remember, all those coinage metals were in the same group: copper, silver, and gold. The element with the symbol Pb, Pb stands for plumum. The ancient Romans made their plumbing from lead. And our protons, neutrons, or electrons found inside the nucleus, and of course that would be protons and neutrons. And which of these subatomic particles carries a positive charge? Protons. And which element has 35 protons? Well, as we look at our periodic table, element 35, Br, that's bromine. And what are the number of protons, neutrons, and electrons in silicon 26? Well, first the protons, and we go to the periodic table, and we see the atomic number for silicon is 14. The neutrons, well, that's the mass number, 26, minus the protons, 14. And then our electrons would be the same as the number of protons, since this is a neutral atom. And the number of protons, neutrons, and electrons in the iron 3 ion, well, when we go to the periodic table and see iron has an atomic number of 26. What about the neutrons? Well, they don't give us the mass number, so we can't answer that. And what does that plus 3 mean? Does that mean we gained 3 electrons? No, we lost 3. Remember, by subtracting negatives, we become positive, so 3 less than the 26, or 23 electrons. And the name of the noble gas in period 3, noble gases, those are the far right column, period 3, argon. And the halogen in period 4, halogens are group 7A. Cross period 4 with 7A. and we get bromine once again. And now, what is the expected formula form from sodium and chlorine? Well, sodium forms a +1 ion, chlorine forms a -1 ion. So bonding number 1, bonding number 1. Here's step 1, identify your participants and their bonding numbers. Step 2, our easy step, the least common multiple of 1 and 1 is 1. Now, what's that 1 tell us? For an ionic compound, that says +1 is balancing -1. So 1 sodium gives us +1. And 1 chloride, we'll find the name of the chlorine ion is chloride, gives us -1. Magnesium forms a +2 ion, chlorine still -1. There's our bonding numbers. Least common multiple of 2 and 1 is 2, which again means +2 is balancing -2. So I'm going to need 1 magnesium for +2 and 2 chlorides for -2. For aluminum and sulfur, aluminum, Al, it's going to form a +3 ion. Sulfur is going to form a -2 ion, so there's my bonding numbers. Least common multiple of 3 and 2 is 6, and what's that 6 tell us? +6 is balancing -6, and hence 2 aluminums are needed and 3 sulfides. Hydrogen and oxygen. Hydrogen wants to form 1 bond, so bonding number 1. Oxygen wants to form 2 bonds, so bonding number 2. Least common multiple of 1 and 2 is 2. And this time, this is a molecular compound, and so that 2 tells us the total number of bonds formed. So it's still your your bonding number into the least common multiple. So 1 into 2 says 2 hydrogens, and 2 into 2 says 1 oxygen. How many covalent bonds does nitrogen want to form? Well, nitrogen wants 3 more electrons to be like neon, and it's going to form 3 bonds to do so. And now the formula of sodium sulfide, containing the sodium ion and the sulfide ion, well, those charges are our bonding numbers. Least common multiple of 1 and 2 is 2. And for +2, we need 2 sodiums. For -2, we need 1 sulfur. Or 1 sulfide, since it's now in a -2 state. We'll be talking about the names of ions here in just a little bit. For lithium and bromide, lithium has a +1 ion, so bonding number 1, bromide, -1 ion, bonding number 1 again. Least common multiple of 1 tells us +1, which takes 1 lithium. This is balanced by -1, which takes 1 bromide. Then we have the calcium ion, which is +2, so bonding number of 2, and the oxide ion, -2, so bonding number of 2. Least common multiple of 2 and 2 is 2, so +2 is balancing -2. So how many calciums for +2? And how many oxides for -2? And no, you don't have to put the ones in, but I'm just illustrating that there be 1 of each. Okay, on to the names of compounds, and we're going to start with ionic compound names. And the ionic compound, we have the name of the positive ion followed by the name of the negative ion, which means we need to begin by learning the names of the ions. We're going to start with what are called the simple ions, which are a single element ion, and the simple of these would be the negative ions. For a negative ion, so we're talking about the nonmetals, remember nonmetals want to gain electrons, we would have the root name of the nonmetal plus "ide." You already heard me refer to chloride and oxide, and with nitrogen in a -3 state we have nitride. So again, the root name plus "ide." And you'll get a feel for the root names, don't worry about it. With practice we'll just get those down, so don't feel like you got to force this. Then for the positive simple ions, these are the metals, and we have 2 different types. We have a singly charged metal, which is just the name of that metal, and then we have the variably charged metals, meaning they have more than 1 charge. If we have more than 1 charge, we have to give that charge as part of the name. So iron can form a +2 ion and a +3 ion. So we have the iron 2 ion and the iron 3 ion. And again, we give those charges as Roman numerals. Then for lead, we have a +2 ion for lead 2 and a +4 ion for lead 4. So when we have variably charged metals, in a moment we'll talk about which ones are variably charged, we need a Roman numeral. If we have a constant charge, so for example, potassium is always +1, we don't need the Roman numeral if it's a constant charge. Okay, where are the variably charged metals and the constant charge metals? Where our main group, or our S block metals, are going to have a constant charge. So everybody in group 1 is always +1, so we don't have to say sodium 1, we don't have to say potassium 1. And the elements in group 2A are always +2, so we don't need to say magnesium 2 or calcium 2. So for these, we don't need a Roman numeral, simply the name of that metal. Then all of the rest of the elements, so essentially from group 2 all the way to the zigzag, these need a Roman numeral. So all of those D block and F block, or should I say the majority of our D block and F block elements need a Roman numeral, and even some of those that squeeze over up against the zigzag. Now, there are a few that have a constant charge that we need to know the names of, that they have a constant charge. And they essentially all come from the same part of the periodic table. The first is silver, which is always +1. In the next column, we see zinc and cadmium, which are always +2. And then in the next column, we have aluminum, gallium, and indium, which are always +3. And gallium and indium weren't even on our list of elements to know the names. But do note, silver is 1 high, zinc and cadmium, that's 2 high, aluminum, gallium, and indium are 3 high. So silver +1, zinc and cadmium +2, aluminum, gallium, and +3. So +1, +2, +3. This little triangle have constant charge, so we don't need to give them Roman numerals. So it's just silver, not silver 1. Just zinc, not zinc 2. Just aluminum, not aluminum 3. Then there are the polyatomic ions, and this is going to make this a little bit more complex. Essentially, the majority of these, fortunately, are oxoanions, where there's a regular pattern that we can learn, which essentially will help us from having to just simply memorize these formulas. I'll be going over that in a moment. Now, the oxoanions. Now, these all contain some nonmetal and one or more combinations of oxygens. Later we're going to talk about the oxoacids, and we'll see that the oxoanions and the oxoacids are related. For now, let's just talk about the oxoanions. If we have just one oxoanion, it's going to get this suffix of 8 to tell us we have that one. So you've heard of sulfate and nitrate and phosphate. If we have 2, then the one with the greater number of oxygens has the 8 suffix, and the one with the lesser number would have an ite suffix. Now what if we have even more oxygens, or less? Well, we have one more than the 8 suffix, then we have a per that's going to sit out front, as in perchlorate. And if we have one less than the ite, then we have hypo sitting out in front, and so there's hypochlorite. Now we really only need to know how many oxygens gets the 8 suffix, and then we can determine how many based on the additional suffixes. Or if we have a different number of oxygens, we can determine what is our new suffix and if there's a prefix. So that relationship is, if we have one less oxygen, we have the ite suffix. If we have 2 less oxygens, then we have a hypo as a prefix and an ite as our suffix. So the fewest would be a hypoite, then ite, then 8. If we have even more than 8, one more than 8, we use the prefix of per. So we have per and 8. So at the bottom we would have ite, then at the bottom we have hypo and ite, then ite, then 8, then per and 8, and we'll see this in this table here. So look over here on the left and we say ClO negative, ClO2 negative, ClO3 negative, and ClO4 negative. The one with 1 oxygen is hypochlorite. The one with 2 is chlorite. The one with 3 is chlorate. And the one with 4 is perchlorate. But we only need to know that the one with 3 had the 8 suffix. So ClO3 has the 8 suffix, so that's chlorate. So if I see 1 less oxygen, I know that's chlorite. And if I see 2 less, then it has hypo and ite for hypochlorite. If I have even 1 more than 8, then I get the prefix of per for perchlorate. So again, all we need to know is how many oxygens gets the 8 suffix. 1 less ite, 2 less hypo and ite, 1 more per and 8. Over on the right, we see the parent acids and their names, and they still have the hypos and pers if needed. But instead of ites, we have us, and instead of eights, we have ix. Let's see, since you just know that, and don't worry about that, because we're going to talk about this more in a little bit. So for right now, let's just pay attention to the ones on the left. The ions, the oxoanions, the eights and the ites, the hypos and the pers. Okay, so it sure would help if we knew how to determine how many oxygens get these 8 suffix, and we can determine that by using the periodic table. For the elements that are in period 2 or group 7A, these elements have 3 oxygens to get the 8 suffix. Anybody else would have 4. So here's our periodic table, and there's the 7. Period 2 in group 7A, note it forms a 7. Period 2 and group 7A. It looks like a 7. The elements in that 7 have 3 oxygens for their 8 suffix. So borate has 3, carbonate has 3, nitrate has 3. There isn't an oxoanion for oxygen or fluorine. Chlorate has 3, bromate has 3, and iodate has 3. Acetine is radioactive, so we don't see that guy show up much. Okay, so in the 7 we have 3, and what if you're outside the 7? We have 4. And it's a coincidence that 3 plus 4 is 7, but it's either 3 or it's 4. In the 7 it's 3, outside the 7 it's 4. So how many oxygens does phosphate have? Outside the 7, 4. How about sulfate? Outside the 7, 4. How about chlorate? In the 7, so 3. So this is how we can quickly determine how many oxygens gets the 8 suffix. And then if we have even 1 less, then it would be an ite. 1 more, it's a per and an 8. 2 less, a hypo and an ite, as we saw in the previous slide. So again, if your non-oxygen is in that 7, it has 3 oxygens for the 8 suffix. Outside the 7, it has 4. Okay, so as an example, what's the name of this oxoanion? Well, I see sulfur, and sulfur is not in the 7, so sulfate has 4 oxygens. I see 1 less, so we go to ite, sulfite. Okay, for this oxoanion, I look for the position of phosphorus in the periodic table, and it also is not in the 7. So that means phosphate has 4 oxygens. I see 2 less, so 1 less is ite. 2 less, you have the prefix of hypo along with the ite. So hypophosphite. Okay, the oxoanion of nitrogen here, well, the nitrate oxoanion, well, nitrogen is in the 7, so how many oxygens does nitrate have? 3. Here we have 1 less, so that goes down to ite for nitrite. You may have heard of nitrites. So again, we begin by asking how many oxygens gets the 8 suffix, and then if we have that number, we have the 8. If not, then we adjust the name accordingly. Okay, we have one more thing to determine, and that is the charge on the oxoanion. Unfortunately, it's always negative, and it's related to the bonding number of the non-oxygen. So, Essentially, it's the bonding number for everybody but carbon and nitrogen, where we would reduce that by 2. Here we see sulfite, and sulfur has a bonding number of 2, so sulfite is -2. Chlorite, well, chlorine has a bonding number of 1, and so a charge of -1. This last one, nitrate, well, nitrogen has a bonding number of 3, but it is one of our 2 exceptions. So we reduce that 3 by 2, and that gives us -1. So it's either your bonding number, unless it's carbon or nitrogen, and this is because they're so small. So if you're not carbon or nitrogen, your charge is equal to your bonding number. If you are carbon and nitrogen, you're going to reduce that bonding number by 2. So nitrate and nitrite are -1. Carbonate and carbonite, there isn't a carbonite, but essentially you would take the 4 and reduce it by 2 for -2. Now there are some other polyatomic ions. These don't necessarily follow a pattern, and so we're going to have to put more effort into learning their names. So here we have chromate. Well, we might have predicted 4 oxygen, but we couldn't have predicted that -2. So we have to remember the -2. Next we have dichromate. The di might have given us the clue that we had 2 chromiums, but now we have 7 oxygens and a -2. So there's going to be at least something that's not predictable about these other polyatomic ions. Then we have the permanganate ion. So we saw per means even more than the 8. But 4 oxygens and a -1, hard to predict. This guy has no real clues at all. Oxalate, 2 carbons, 4 oxygens, and a -2. No real clues at all there. We're going to probably have to spend more effort in remembering that one. Then we have acetate. This is an organic ion, and perhaps you'll be learning more organic chemistry in your future. But anyway, that's why it has carbons, hydrogens, and oxygens, because it's an organic ion. That actually came from acetic acid. That's essentially what vinegar is. Then we have the cyanide ion, and do note, everybody else had an 8 suffix. Here we have an "ide" suffix. Normally, "ide" would mean a single element all by itself. So cyanide and hydroxide are 2 exceptions to that. These are the only 2 that have an "ide" suffix that are a polyatomic ion. Now, fortunately, they both have just 2 elements and a -1 charge. We just need to remember for cyanide, those 2 elements are carbon and nitrogen, and for hydroxide, the 2 elements are oxygen and hydrogen. Then we have our one and only common polyatomic cation. Every other polyatomic ion has been negative. And this is the ammonium ion, not ammonia, but it is related to ammonia, and we'll learn more about that later. So ammonium, NH4 with a positive charge. By the way, ammonia is NH3, no charge. Okay, now when it comes to naming ionic compounds, as I mentioned earlier, it's simply the name of the cation followed by the name of the anion, and it's always written in that order. So name of the cation, it's usually going to be a metal, followed by the name of the anion, could be a nonmetal, could be a polyatomic ion. So as an example, here we have potassium bromide, cation potassium, anion bromide. Now we have calcium as the cation, and what's the name of NO3? Well, how many oxygens does nitrate have? Well, nitrogen is in the 7, so that is nitrate. Altogether, calcium nitrate. Now, sometimes we have those variably charged metals, and how do we determine what the charge is? Well, essentially, we always know the charge on the anion, and so whatever charge ends up balancing it. So here in Fe2S3, each sulfide is -2. So 3 -2s is -6, which has to be balanced by +6. So each of those irons must be +3. So that's iron Roman numeral 3 sulfide. And I'm going to show you 2 ways to determine that charge. One is algebraically, so we can say the sum of the iron charges in the, actually that's to be sulfur, so replace that O with an S. So essentially the sum of the 2 iron charges and the 3 sulfide charges is equal to 0. Essentially the charge must balance, they must add to 0. Can't have leftover charges. Then we know the charge on the anion, that's -2 for sulfide. And so our 2 irons plus 3 -2s is equal to 0. Let's just go ahead and distribute that. So our 2 irons minus 6 is equal to 0. Let's add 6 to both sides. So the 2 irons have a total of plus 6. So each iron must be plus 3. So there's the plus 3 that we got for iron 3 sulfide. And this is one way, the algebraic way, and it always works. It's a little bit more work than the other way. I'll show you the other way in just a little bit. But we have one more example, and here we have lead, Roman numeral 4 oxide. Lead's one of those elements that needs a Roman numeral. And do note each oxide is -2, so that must be a positive 4 lead that's balancing the 2 -2s in the 2 oxides. And I'll show you that other method of determining charge in just a little bit. Okay, let's do some more examples. Name the following, and first we see a cation and an anion, so we know it's ionic. And the name of our cation is silver. Does silver get a Roman numeral? No, it's part of that triangle that has constant charges, so simply silver. And the name of the anion, well, sulfur all by itself is sulfide. All together, silver sulfide. Okay, let's name this compound. Well, I see it's ionic because I have a metal and a polyatomic ion. What's the name of that metal? Well, that's potassium. Does potassium get a Roman numeral? No, it's a group 1A metal, so it's always +1, and so just simply potassium. What about the name of the anion? Well, we would begin by asking how many oxygens does phosphate have? Phosphorus isn't in the 7, so phosphate has 4 oxygens. So this one with 1 less is phosphite. Altogether, potassium phosphite. Okay, we have an ionic compound. I see a metal. What's the name of that metal? Pb is lead. Does lead get a Roman numeral? Yes, it does, and I'll show you in a moment how to get that. Let's finish off. What's the name of our anion? Well, nitrogen all by itself is nitride. Again, a single element is ide. The ites and the ates, the ones with the T's, have oxygens. Okay, now, what is the expected charge on the nitride, on just one of them? Well, nitrogen wants 3 more electrons to be like neon, so it wants to be a -3 ion. Okay, that's 1 nitride. Note how I wrote that -3. But there's 4 of them, so we have a total of -12. Okay, now why did I need to know the total was -12? Because now it tells me the total positives, and that must be +12. Again, our charges balance in an ionic compound. Our positives are equal to our negatives and vice versa. Okay, so we have a total of +12, but we have 3 leads. So let's divide that 12 by 3 to tell that each lead is +4. For lead, Roman numeral 4, nitride. So this is the shorthand method for determining the charge on those variably charged metals. Okay, the name of our cation, manganese. Does manganese get a Roman numeral? Yes, it does, so we leave an empty spot behind for it. The name of our anion. Well, how many oxygens does nitrate have? Well, we look at nitrogen in the periodic table, and it is part of the 7. So nitrate has 3 oxygens, so this is nitrate. Now we need the charge on nitrate, so that comes from the bonding number of the nitrogen. Note that the charge on the polyatomic ion does not come from the number of oxygens. So nitrate, well, nitrogen has a bonding number of 3, but it's one of our 2 exceptions. So remember, we reduce the 3 by 2 to get a 1. Again, -1. They're always negative. Okay, each nitrate is -1. By the way, nitrite will be -1 too. Doesn't matter how many oxygens, as I mentioned. Two negative ones is -2, telling us the charge on the manganese is +2. Manganese, Roman numeral 2, nitrate. Okay, naming binary molecular compounds. This is actually quite a bit simpler than ionic compounds, where we use a prefix system to indicate the number of each element in the compound. We just need to know what are those prefixes. Well, if we have 1, we have mono. I imagine you're familiar with this. Now, we usually omit the mono unless it's somebody that's not really expected, like carbon monoxide. We expect carbon to have 2 oxygens. 2 is di, as in carbon dioxide. 3 would be tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 would be nona. And if we ever do get up to 10, it would be deca. So we just need to know what these prefixes are, and by far the smaller numbers are the more common. Let's do a few examples. And so in F3, well, that's nitrogen, trifluoride. We still use that "ide" suffix with the last element. So what would this be called? Dichlorine oxide. Carbon with 4 chlorines would be carbon tetrachloride. Two nitrogens and 5 oxygens would be dinitrogen pentoxide. We might be tempted to call it pentaoxide, but when we have oxide, we essentially drop the A at the end of penta or hexa, hepta, whatever. Okay, I hope you find naming binary molecular compounds pretty straightforward. On to naming acids. Well, acids come in 2 forms. We have binary acids, where we would have a hydrogen and some non-oxygen, some non-metal. Now, I want to point out that to be an acid, we are going to be able to form hydrogen ions. So binary acids are essentially hydrogen bound to some non-oxygen, some non-metal, that essentially where that hydrogen can be kicked out without its electrons. When we see one of these, we use the prefix of hydro. Still the same root name of your non-metal, and then this suffix of ic acid. So you may have heard of hydrochloric acid. That's one example. Okay, now we'll see some examples of some pure substances and this new name when they're placed in the water. So HCl all by itself is hydrogen chloride, using our normal binary molecular rules. HBr, hydrogen bromide. HI, hydrogen iodide. But when we put them into water, then they can kick out that hydrogen while stealing the electron. At that point, we give them this new name and treat them or name them as an acid. So we have hydrochloric acid for HCl in water, hydrobromic acid for HBr in water, and hydroiodic acid for HI in water. And that AQ essentially refers to a water-based solution. Essentially, it refers to aqueous. Then we have oxoacids, and these are the parents of the oxoanions. And there's a relationship between their names. Those 8 ions end up coming from a parent ic acid, and the 8 ions came from a parent us acid. So we simply need to remember 8 ions come from ic acids and 8 ions come from us acids. And then we can use what we've already learned about 8s and ites, those oxoanions. Okay, so in this first example, ClO3 negative is chlorate. So the parent acid, and do note we have a hydrogen for each negative charge, so we have HClO3. Well, that's chloric acid. No, ic acids form 8 ions. 8 ions are formed from ic acids. ClO negative is the hypochlorite ion. So the parent acid is the hypochlorous acid. So we're simply just replacing the suffix at the end of the name. We might still have the hypo and the per. We already know how to name the oxoanions, so we take advantage of that, and now we know how to name the parent oxo acids. Okay, back to that table we saw earlier, and over on the left we had the oxoanions, and over on the right are the oxo acids, and we can see how the ite ions came from the us acids. So hypochlorite came from hypochlorous acid. Chlorite came from chlorous acid. And the 8 ions came from the ic acid. So chlorate came from chloric acid, and the perchlorate ion came from perchloric acid. We're simply replacing ites with us and eights with ics. Okay, let's practice some of the things that we have learned here today. First, what is the octet rule? And that's essentially the same as the noble gas rule, which states that all elements want 8 outer electrons. All elements want the electron configuration of their nearest noble gas neighbor. And now, what is the formula of the simple ion formed by magnesium? Well, magnesium belongs in group 2A, so that means it has 2 outer electrons, which it's going to lose to go back to the last noble gas, and hence it has a positive 2 charge. If you ever get confused on what the charge is, well, magnesium has lost 2 electrons to be like neon with 10 electrons, but it still has 12 protons. 12 protons, 12 positives, 10 electrons, 10 negatives. That's 2 more positives than negatives. So we can always go back to basic principles to determine the charge. And now give the formula simple ion formed by iron. Well, we can't answer that. Iron is one of those variably charged metals. Now, if we're given the formula of a compound with the iron in it, then we could deduce the charge, but just by being asked what is the charge on iron, we don't have any way to tell. And now, what is the charge of the simple ions formed by group 6A? Oxygen is an example of a group 6A element, and everybody in group 6A wants to gain 2 electrons to be like the next noble gas. Gaining 2 electrons means they have a negative 2 charge. Now I'll give the formula of the ionic compound containing the aluminum ion and the chloride ion. Well, those charges are our bonding numbers. And the least common multiple of those bonding numbers gives us the total positives and the total negatives. So again, bonding number 3, bonding number 1, least common multiple of 3 says positive 3 is balanced by negative 3. So 1 aluminum for positive 3 and 3 chlorides for negative 3. And what is the formula of the ionic compound containing the cesium ion and the carbonate ion? Well, we would do the same thing for polyatomic ions as we do single element ions. That +1 on cesium means it has a bonding number of 1, and that -2 on carbonate means it has a bonding number of 2. Least common multiple of 2 says positive 2, which is going to take 2 cesiums, is balanced by -2, which requires a single carbonate. So the same method for determining the formulas of single element ion compounds. And now the formula compound containing the iron 3 ion and the selenate ion. Note I had to call that iron 3 because iron can have more than 1 charge. And that was selenate. Selenium is not in the 7, so its 8 suffix gets 4 oxygens. Okay, well, I have right in front of me what I need, the bonding numbers 3 and 2. So that gives me the least common multiple of 6. And what's that 6 telling us? Positive 6 is balancing -6, and hence 2 irons and 3 selenates. Now note, since I had more than 1 polyatomic ion, I had to include the formula within parentheses with a subscript outside telling us how many were in that formula. And now, what is the formula of the cyanide ion? Well, I normally means a single element all by itself. But is there a cyano element? No, this is one of those two polyatomic ions that had an I suffix. You may recall that they both had two elements and a -1 charge. For cyanide, the two elements were carbon and nitrogen. The other one would have been hydroxide with oxygen and hydrogen, -1. Sulfide, well, there is a sulf element, sulfur, with its expected -2 charge. And now the formula of the nitrate ion. Well, anything has nitrogen. Eights and ites also have oxygens. And we look for the position of nitrogen in the periodic table to see nitrate has 3 oxygens. Nitrogen's in that 7, period 2, in group 7A. We now just need the charge. The charge comes from the bonding number of nitrogen. Bonding number of nitrogen is 3, but it's one of our 2 exceptions, so we reduce that 3 by 2 for a charge of -1. So again, determining the formula of a polyatomic ion, we need to just come up with 2 things, the number of oxygens and the charge. And now, what is the name of this ionic compound? Well, the name of the metal, barium. Does barium get a Roman numeral? No, it belongs in group 2A, so just barium. And now the name of the anion, well, nitrogen all by itself is nitride. Single element, suffix ide. Ites and eights, the ones with the T's, have oxygens, as you see for nitrate above. And what's the name of this compound? Well, what's the name of our cation? Iron. Does iron get a Roman numeral? Yes, it does. We'll figure it out in a moment. Name of the anion, oxide. Okay, the charge on a single oxide, -2. So 3 oxides have a total of -6. And that -6 must be balanced by +6. Since there's 2 irons, each is +3. Or iron, Roman numeral 3, oxide. Okay, what's the name of this compound? Well, I see a metal and a polyatomic ion. They both tell me this is ionic. What's the name of that metal? Cobalt. Does cobalt get a Roman numeral? Yes, it does. We'll figure it out in a moment. Name of the anion. Well, how many oxygens does phosphate have? Is phosphorus in the 7? No, so phosphate has 4, and hence that's phosphate. Now, what's the charge on phosphate? Well, what's the bonding number of phosphorus? 3. Is this one of our 2 exceptions? No, our 2 exceptions were carbon and nitrogen. So, -3. There's only one of them, so that's balanced by +3, and hence cobalt, Roman numeral 3, phosphate. Name of this compound? Well, the name of the cation, Sn, is 10. Does 10 go to Roman numeral? It sure does. We'll leave an empty spot behind for it. Name of the anion, oxide. And the charge on a single oxide is -2. 2 -2s is -4. Of course, -4 is balanced by +4. Or 10, Roman numeral 4, oxide. And what's the name of this compound? Well, what's the name of our cation? Silver. Does silver get a Roman numeral? No, it's part of that triangle. Name of the anion, sulfide. All together, silver sulfide. And the name of this compound, well, what's the name of our cation? Potassium. Does potassium get a Roman numeral? Nope, group 1A, always +1, so just potassium. And now the name of our anion. Well, how many oxygens does phosphate have? 4. So this is phosphite. And the name of this ionic compound, well, what's the name of our cation? Lead. Does lead get a Roman numeral? Yes, it does, so leave an empty spot behind for it. And now the name of the anion, well, nitrogen all by itself is nitride. So lead, Roman numeral, nitride. What's the expected charge on a single nitride? -3. 4 -3s would be -12. And -12 is balanced by +12. So each lead must be +4. For lead, Roman numeral 4, nitride. Okay, what's the name of this compound? Well, what's the name of our cation? Manganese. Does manganese get a Roman numeral? Yes, it does. We'll leave the empty spot behind for it. The name of the anion, well, that is nitrate. The 8 suffix for nitrogen has 3 oxygens. Now, what's the charge on 1 nitrate? Well, we get this from the bonding number of the nitrogen. The bonding number of nitrogen is 3. Is this one of our 2 exceptions? Yes, it is. So we reduce that 3 by 2 for a charge of -1. 2 -1s is -2, which is balanced by +2. There's only 1 manganese. So manganese, Roman numeral 2, nitrate. Now the formula of cobalt-3 sulfide. Well, the cobalt-3 tells us we have cobalt with a +3 charge. And by the way, there's your bonding number. Now, sulfite. Well, sulf and anything has sulfur. 8s and ites also have oxygens. And we will begin by asking, how many oxygens does sulfate have? Well, sulfate has 4 oxygens, so sulfite must have 3. Lastly, we need the charge, and that comes from the bonding number of the non-oxygen. The bonding number of sulfur is 2, and it's not one of our 2 exceptions, so sulfite is -2. Again, those charges are bonding numbers. So bonding number 3, bonding number 2, the least common multiple of 6 tells us, what's that 6 tell us? +6 is balancing -6. And there's our formula of cobalt-3 sulfite. Okay, what's the name of this compound? Well, what's the name of our cation? Zinc. Does zinc get a Roman numeral? It's part of that triangle, so no. It's always +2, so just zinc. And now the name of the anion. Well, this was one on the other list. This was that oddball that I said was really hard to remember. Oxalate. Zinc oxalate. And now, what's the formula of chromium-3 hydrogen phosphate? Well, chromium is Cr, and that 3 gives us the charge. And of course, that means it's its bonding number. Now, phosphate has 4 oxygens. Now, what does that mean to have a hydrogen in front of the phosphate? Well, that means it also has a hydrogen. So, not just PO4, but HPO4. Now note the charge is not the -3. Bonding number of phosphorus is 3, and it's not one of our 2 exceptions, so phosphate would have a charge of -3. Why does this have a -2 charge? Because that hydrogen was the parent, or excuse me, was part of the parent acid, and it didn't get rid of all 3 hydrogens. The charge ultimately comes from the hydrogens that are kicked out. And so it only got rid of 2 hydrogens, not all 3. That's why we have the -2 charge. So if you have a hydrogen left, you're going to have 1 less negative. 2 hydrogens, 2 less negatives. Okay, bonding number 3, bonding number 2, least common multiple of 6 tells us +6 is balanced by -6. And there's our formula for chromium 3 hydrogen phosphate. Okay, let's name this oxo acid. Well, let's put our thumb over that hydrogen and ask, what's the name of that daughter ion? Well, how many oxygens does bromate have? 3. So there's bromate. And 8 ions come from ic acids. So bromic acid. And now what's the formula of aluminum dichromate? Well, we see that aluminum is going to have a +3 charge. Dichromate, well, we need to remember that formula. And that formula was 2 chromiums, hence the di, and 7 oxygens, and a -2 charge. There's our bonding numbers. Bonding number 3, bonding number 2. Least common multiple is 6 again. And we know that 6 tells us +6, which takes 2 aluminums, is balanced by -6, which takes 3 dichromates. And now what's the name of this? Ionic compound. And how do I know it's ionic? Because it begins with a metal and I see a polyatomic ion. Okay, what's the name of that metal? Iron. Does iron get a Roman numeral? Yes, we'll leave an empty spot behind for it. Finishing off, what's the name of the anion? Hydroxide. And hydroxide has a charge of -1. So those 3 -1s is -3, telling us the charge on the iron is +3. For iron, Roman numeral 3, hydroxide. And the formula of potassium nitride. Well, potassium is a group 1A element, so K+1. Nitride, nitrogen's a group 5A element, and it wants 3 electrons, so -3. There's our bonding numbers. Bonding number 1, bonding number 3, least common multiple of 3 tells us +3, which is going to take 3 potassiums, is balanced by -3, which is a single nitride. And now what's the name of this compound? Well, first, is it ionic or covalent? Well, if that first element, selenium, is a metal, it's ionic. If it's a nonmetal, then it's covalent. Is selenium a metal? No, it's on the nonmetal side, so it's covalent, so we use the prefix system for selenium tetrafluoride. Now notice, selenium was a metal. This would either be selenium fluoride or selenium Roman numeral 4 fluoride. Ionic compounds have totally different names than molecular compounds. And I would point out that the mono, di, tri, etc. is not ever part of a ionic compound. The charges tell us the elements in it or the ratio of ions in it. Okay, that's the end of our lecture where we learned about compound names, beginning with ionic compounds. And ionic compounds contain ions, and they're named with the name of the cation, followed by the name of the anion, and so we spent a lot of time learning the names of the individual ions. We then learned about our molecular binary compounds, where we use the prefix system to indicate how many of each. And then we learned to name acids. We had 2 types. Binary acids, where we had hydro, and do note, hydro, no oxygens. If there's oxygens, there's never a hydro. And for oxoacids, they had a relationship to the oxoanions, and that would remind you that ic acids form 8 ions and us acids form 8 ions. And one of my students told me the way to remember ic and 8 is I ate something icky.